Hello and welcome. My name is Michael Healy, and today I'll be presenting Bench Scale Studies, Lessons Learned from Informing Field Demonstrations. Before we get into the presentation, though, I'd like to take the time to thank my co-authors Sandra Dworczyk, Phil Dennis, and Jeff Roberts. At some point in the life of every site, there comes a point when it's time to decide on a remediation strategy. But before that strategy can be determined, there are two key questions that must be answered. The first is, what is the best remediation approach for the site? And the second is, once implemented, is the remediation strategy working? The focus of this presentation will be on answering that first question and determining the best remediation approach before you move to full-scale implementation. One of the best tools for selecting the appropriate remedy for the site are bench scale or treatability studies. What is a treatability study? Well, it's a small-scale test using site soil, sediment, rock, or groundwater mixed together in either a batch system or in a flow-through column that is used to monitor contaminant degradation under a variety of conditions using different remedies that could be applied at the site. Treatability studies allow for customized treatment variables to meet site-specific needs. Almost any technology that can be used in the field to remediate a site can be tested using a bench-scale treatability study. At Sirem, we've tested a variety of technologies, including anaerobic and aerobic bioremediation, in situ chemical reduction using compounds like ZVI, in situ chemical oxidation using compounds like permanganate, peroxide, or base-activated persulfate. You can even do studies looking at sorptive medias like GAC or zeolite, or you can even look at in situ stabilization with the addition of cement or mixtures of some of these technologies together. So what can a treatability study actually tell you? Often it can tell you electron donor, acceptor, or co-metabolite consumption if you're looking at a bio study. You can see degradation intermediates or pathways that may appear if you're using a specific technology. They can also let you know on what different variables and how controlling those variables is going to impact the remediation at the site. And that's looking at things like pH, ORP, different amendments that you might be looking at, inhibitory effects or competition effects between two sites, or even what type of persulfate activators or oxidant demands might be available at the site. If you look at column studies, you can also look at residence time or the longevity for permeable reactive barriers, and you can also get a better sense of contaminant degradation rates and lag times. In addition to gaining technical information for a given remediation strategy, treatability studies can also provide many other benefits, including evaluation of multiple technologies, optimization of a selected remedy, for example, selecting a specific dose for a given technology. Treatability studies also allow for flexible design, allowing you to change your scope on the fly in the lab if a given technology is not working. For example, an anaerobic bioremediation study could be changed to an aerobic bioremediation study if degradation of the compounds was not being observed under anaerobic conditions. Treatability studies also allow for manageable incremental risk as you move from a lab scale to pilot scale to full scale, with each step informing the next one along that ladder. And finally, treatability tests can act as a form of insurance that allow stakeholders to feel more secure that the remediation approach that was selected is feasible prior to field implementation, and that the money that they're spending is going to be well spent. Before we get into a couple of case studies that demonstrate how treatability studies can impact a field study, I'd like to go through the two major types of treatability studies or bench scale studies that you can complete: batch reactors and flow-through columns. Batch reactors are constructed of small bottles that are mixed with soil and groundwater, or sometimes just with groundwater and sometimes just with soil. These allow to test multiple technologies with small sample volumes from the field. Generally, they are a closed system, which means that everything that happens inside the bottle stays inside the bottle, and they can be less expensive to run than a column study. The drawbacks to a batch reactor, however, is that closed system can often exacerbate inhibitory effects that you might see, for example, inhibition by ZVI for a bioremediation study, or they can also show you results that might be more impressive than what you might see in an open system, or that result in less ideal conditions. The alternative is looking at a flow-through column. And in a flow-through column, generally geologic material, or if you're looking at a PRB, is packed into a tube with sampling ports along that tube, and groundwater is pumped through the column. This way, you can look at changes in the geochemical makeup of the groundwater as it flows through the remedy or through the geologic material, and can provide more detailed design data on the given technology that you're testing. You can also even obtain estimates on the treatment longevity that you might see in the field. However, flow-through columns tend to be more expensive than an average batch test. That being said, you can also compare the two technologies by using a batch system to test multiple technologies together, maybe looking at bioremediation, ISCR, and ISCO in a batch test, and then moving to a column study using only the most effective technology from the batch test to get more detailed design data. With all that in mind, let's jump into a few case studies that demonstrate how bench scale studies impact field scale implementation. Our first case study today looks at anaerobic bioremediation of chlorinated ethenes and ethanes. Our first site was a former gold leaf manufacturing facility that operated from 1955 to 1985, with many solvents used in its production processes, including 1,1-DCE, 1,1-DCA, benzene, vinyl chloride, 1,1,1-TCA, and xylenes. In the early 2000s, the site was redeveloped to house medical operations and offices, and in 2009, the new owner completed groundwater investigations, which led to further groundwater well installation in 2011 and an RAW being issued for bioremediation in 2015. Before the field implementation was put into place, the operating consultant wanted to confirm that anaerobic biodegradation was going to be a viable remediation for this site. As a result, a bench scale study was designed, looking at degradation of mixed chlorinated and ethenes using an anaerobic sterile control, anaerobic active control, a biostimulation treatment, which basically is where you add electron donor and nutrients that will stimulate the appropriate anaerobic bacteria to grow and eventually degrade those compounds. And finally, a bioaugmentation treatment, which was amended with the same electron donors and nutrients, as well as a bioaugmentation culture, in this case KB1+, that contained many bacteria responsible for the anaerobic degradation of these chlorinated solvents. Additionally, sodium bicarbonate was used in this site to adjust the pH as the pH changed over the course of the study. So the results from the sterile control, active control, and biostimulation treatment all told the same story. Nothing happened. Concentrations of 1,1-DCA, 1,1-DCE, and 1,1,1-TCA remained stable throughout the course of the study. The bioaugmentation treatment, however, told a different story. Concentrations remained stable in the treatment until after bioaugmentation on around day 30. After that, concentrations of 1,1-DCA and 1,1,1-TCA were degraded to chloroethane, which is the least chlorinated end product for that particular degradation pathway, and 1,1-DCE was dechlorinated to vinyl chloride and ethene. Over time, we eventually saw some rebound of the concentration of 1,1-DCE, so as a result, the microcosms were bioaugmented again around day 115 to further reduce the 1,1-DCE concentrations and remaining vinyl chloride concentrations. Although complete dechlorination wasn't observed, what we did see was very positive signs that bioaugmentation was required to promote complete dechlorination of 1,1-DCA to chloroethene and 1,1-DCE to ethene. And based on these study results, enhanced bioremediation was confirmed as the site remedy. So in 2016, a field scale remediation was put in place. A modified injection scope had to be used to do the sensitivity of on-site operations. As I mentioned, this was a medical facility that also had offices that were actively being used. Pilot test was used to confirm the injection depths, as there was some complicated geology that had to be dealt with. But eventually, full-scale implementation included 27 temporary injection points over a 36,000 square foot area, with over 1,000 gallons of EDSER, which is an emulsified vegetable oil product, 216 gallons of nutrients, which is a product that's designed to provide essential nutrients to bacteria, 54 liters of KB1+ bioaugmentation culture, and over 9,000 gallons of anoxic water were injected into the aquifer. So what we're seeing here are some results from a monitoring well that was right in the center of the remediation area. What we can see is that the dotted line is where all of those injections take place, and we can see concentrations in the aqueous phase of the groundwater increase after all of those amendments were weighed. What this showed us was that much of the mass was sorbed to the geologic phase in this site, and that after we applied the emulsified vegetable oil and bioaugmentation culture, some of that material was mobilized into the aqueous phase. But what we also see is that shortly after the mobilization, concentrations began to decrease dramatically, along with increases in the overall gene copies of Dehalobacter, which is the bacteria responsible for 1,1,1-TCA, 1,1-DCA degradation to chloroethane, and increases in the copies of vinyl chloride reductase, which is the gene responsible for the degradation of 1,1-DCE and vinyl chloride to ethene. We also see that over time, the concentration of chloroethane increased as the concentration of 1,1-DCA and 1,1,1-TCA decreased over time, which lets us know that there's likely anaerobic bioremediation occurring as that compound is generated in the anaerobic degradation of TCA and DCA. Over time, the chloroethane also decreases in concentration, as that is a compound that is readily degradable under aerobic conditions. From this example, we were able to show that the treatability study indicated that bioaugmentation was the only way we were going to see complete dechlorination of the chlorinated ethenes and ethenes at this site. We were also able to show that EDSER and Nutrimins were able to create the appropriate reducing conditions required for anaerobic bioremediation to occur. Interestingly, we also saw that after the injections in the field, we saw an increase in the aqueous concentration of the CVOCs, indicating the release of sorbed mass from the geologic material at the site. But with those increases in the CVOC, we also saw increases in Dehalobacter, which correlated with decreases in the chlorinated ethanes with time. All that being said, the increased CVOC concentrations in the aqueous phase did not translate to increases in the subslab or indoor air concentrations of VOCs that were detected and monitored for around the site. This site is still currently under remediation and is still currently cleaning up the chlorinated VOCs, but over time, as the CVOCs are fully eliminated, the system may be switched to an aerobic system to treat the remaining benzenes and xylenes that are still present in the site groundwater. Our second case study is going to look at a site that was using PAC, or powdered activated carbon, to sequester PCBs that moved from a bench scale study to a full-scale field implementation. So a little bit of background on that site. This was from an active waterway site in California with PCB contaminated sediment. The solution to stopping the PCBs from leaching out into the pore water or into the surface water was to look at an active thin layer sand cover mixed with powdered activated carbon. The consultant for this site needed to know, though, what dose of powdered activated carbon should be added to the sand cover to reduce the overall mobility of the PCBs. After literature review, they suggested an effective PAC dose of between 3 to 10%, and were originally going to use a 10% dose of powdered activated carbon in the cover. However, they eventually decided to do a treatability test to refine that required dose and determine if they actually had to add 10% of activated carbon. A treatability study was designed that used site sediment, site surface water, sand, and powdered activated carbon applied at a range of doses from 0 to 10%. The treatment target for the treatability study was to reduce the pore water concentrations of PCBs by 75% using the different doses of PAC. To monitor the pore water concentrations in the reactors, an SP3 sampler, which is a polyethylene-based passive sampler, was used to measure freely dissolved concentrations of PCBs in the test reactors. It's important to note that the sampler only measured dissolved PCBs and not sorbed PCBs, as PAC does not destroy the compounds it treats, but does sorb them strongly, immobilizing the contaminants of interest and preventing them with interacting with the environment. Results from the absorption treatability study indicated that even at very low doses of PAC, we were able to achieve the target of a 75% reduction in PCB concentrations in the water. In fact, even a 1% dose would have worked to achieve the goal. However, we were also able to see that a 3% dose was just as effective as a 10% dose at reducing concentrations of PCBs by 98% in the pore water. As a result, for the field implementation, a 3% dose of PAC was selected for use, which saved the consultant approximately $375,000 in unused PAC that they could then save as cost savings and pass those on to the client. As a result of the outcomes of the treatability study, a sand cover with a 3% PAC dose was applied at the site. After a 1-year post-remedy monitoring event was completed, confirming that PCB concentrations had been reduced by at least 75% in the pore water, the client received a notification of no further action from the regulator, effectively closing the site. So now we're going to move to our third case study, which looks at ISS and ISCO combined together and how that moved through an initial bench test through to a pilot scale and then a full-scale field implementation. Our third site is a site in Denmark that was contaminated with high concentrations of coal combustion residuals that have been marked for redevelopment. But before redevelopment could occur, the CCR waste had to be dealt with. A novel approach was selected to decrease the contaminant mass using activated persulfate and then immobilize the remaining mass using cement. One of the main functions of the treatability study was to determine if the persulfate and the cement would have to be applied sequentially or if both could be applied simultaneously. Performance targets for the study included reducing the leachable concentration of the coal tar constituents from the material, achieving a minimum hydraulic conductivity of less than 1 × 10⁻⁶ centimeters per second, and achieving a minimum strength of 0.15 megapascals after a 28-day curing period with the cement. Bench test results were able to show that ISS and ISCO would both be effective at removing the contaminants and at reducing the leachability of the compounds present. Results of the ISS plus ISCO combinations, both in the simultaneous and sequential steps, were also able to show that we were able to achieve all of the minimum target metrics for a successful test under both conditions. And due to the speed at which the site had to be remedied and the ease at which it would be to apply both technologies at the same time, a ISS plus ISCO in a simultaneous injection was selected as the field remedy approach. So in transitioning from the bench to the pilot scale, several challenges had to be overcome. The first was that this was the first time this technology was being used in Denmark, which means it was a learning opportunity for the regulators there. There were also several things to consider when moving from the bench scale to a field scale. Additionally, this site was right in the middle of a residential neighborhood, which caused some interesting spatial constraints above ground and some interesting constraints as it regards to proximity to the houses. Additionally, there was some very challenging geology at this site, with 3 to 5 meters of peat above high plasticity clay with a confined aquifer. Additionally, we needed to make sure that the treatment performance was actually being met to those same target values. And they had to handle large quantities of potentially corrosive materials, including cement slurries and persulfate. Based on the results of the pilot test, the following observations and conditions supported a recommendation to proceed to full-scale ISS and ISCO treatment. The average unconfined compressive strength of the samples was 0.86 megapascals. 8 of the 13 samples exceeded the criteria of 0.35 megapascals in the field, and 10 of the 13 samples exceeded the minimum criteria of 0.15. All the samples collected from the deepest portions of the columns exceeded the unconfined compressive strength performance criteria. These results are indicative of the long-term durability of the ISS-ISCO treatment. The 3 samples that failed the minimum compressive strength criteria were all collected from the top of the columns that were used to construct the cement. These samples had issues curing because of the moisture content of the material and stressed that as they moved to the full scale, they would need to have better control of the moisture content in the samples as they were being mixed in the field. For full-scale field implementation, operational improvements and better control of moisture content in the upper portions of the ISS-ISCO mixing columns were implemented to improve strength in the upper portions of the columns. The ISS and ISCO was applied across the approximately 190 meter squared site using a 2-meter diameter auger, mixing 75 cylinders of soil with a 17% overlap with each other. On average, 10 meters cubed per hour of geologic material, cement, and persulfate were mixed together on any given day, with the best days achieving a mixing rate of 36 meters cubed per hour. But there were also many days where no mixing could occur due to several unique field conditions that weren't realized until they were in the field. Some of these caused unexpected challenges, but some also caused some unexpected blessings. The high water content of the soil did increase the overall curing period, and the persulfate solution was quite corrosive, causing some field equipment to break down before modifications could be made to continue with the operation. That being said, the temperatures in Denmark in August are much warmer than temperatures in a typical lab, which resulted in a higher compressive strength being achieved in the field faster than what was ever achieved in the lab QA/QC samples. And as a result, we have now seen a complete remediation of the site, which is currently waiting for development. Our final case study that we're going to be looking at today originally looked at bioremediation at bench scale, which eventually led to an excavation at field scale. The final site is a site from Kansas that had a high concentration of mixed VOCs, including high concentrations of DCM. Two areas of the site were selected for bench scale testing, an area with lower DCM concentrations and an area with higher concentrations. The area with low concentrations, with around 10 milligrams per liter DCM, was able to demonstrate complete dechlorination using a bioaugmentation culture. But the area with higher DCM concentrations was not able to demonstrate bioaugmentation, and also demonstrated that DCM concentrations greater than 160 milligrams per liter would not be biodegradable with the currently available bioaugmentation cultures. As a result, excavation was selected as the remedial approach, and the treatability study justified a faster and less expensive remedy than a potentially futile bioremediation attempt. I would like to note, though, that since this site, the bioaugmentation culture available to degrade DCM has been further developed and could now degrade the concentrations measured at this site. And maybe one day, when the landfill that the excavated material was sent to closes, bioaugmentation could be applied to treat this material. Treatability testing can aid in planning and assessment of full-scale field remediation projects. Often, treatability test costs can be offset by the operational and management savings that result from improved planning and field implementation, and treatability studies can also reduce some uncertainty concerning new remediation technologies and provide data that previews potential field results, making bench-scale treatability studies an invaluable tool for anybody trying to remediate a site. Thank you for your time today. For more information, or if you have any questions, please feel free to reach out to me by email at mhealy@siremlab.com or by phone at 519-515-0852.